You know, inside every big industrial plant, there's a system that's built for the absolute worst day imaginable. It's literally the last thing standing between a smooth operation and a total disaster. Today, we're going to pull back the curtain on how engineers design that final critical line of defense.
So here's the plan. We'll start by really understanding the threat. Then we'll look at three very specific, very tricky engineering challenges and the frankly brilliant ways they're solved. And finally, we'll talk about why these aren't just rules in a textbook. All right, let's set the stage. Any plant, whether it's a refinery or a chemical factory, has to be ready for things to go sideways. And one of the biggest dangers they have to plan for is something called overpressure.
So, what's the big deal? What actually happens when the pressure inside a pipe just keeps climbing and climbing? Well, once it goes past what it was built to handle, the consequences can be, well, catastrophic. That's what we call an overpressure event. Just imagine a balloon being filled with way too much air. The system is literally holding more force than its steel walls can take, pushing it closer and closer to a rupture or, even worse, an explosion. To stop that from ever happening, engineers install this amazing piece of purely mechanical engineering, the pressure safety valve, or PSV. Think of it as a mechanical guardian. It has no computers, no electricity. It's designed to just spring open at one specific pressure, release all that excess energy, and save the day. It is the ultimate failsafe. But here's the plot twist. Our hero, the PSV, isn't perfect. If you don't install it just right, this guardian can become unstable, and that creates a whole new, really serious problem.
So what happens when the one thing that's supposed to save you fails? And we're not talking about it just getting stuck. We're talking about a violent, self-destructive kind of failure. What on earth could go wrong with a simple spring?
It's called valve chatter. The best way to picture it is like a fire hose nozzle that's sputtering like crazy. The valve pops open, the pressure drops for a split second, it slams shut, pressure builds right back up, and it violently hammers open again, over and over, dozens of times a second. This can literally shake the valve to pieces or choke off the flow right when you need it most.
So how in the world do you prevent that? Engineers follow a very simple, very strict rule. And it all comes down to this one little number, 3%. This number is the key to stability. It's called the 3% rule, and here's the deal. It basically says that the pipe leading into the valve has to be big enough and smooth enough so that you lose less than 3% of the pressure due to friction. It's a tiny detail, but it's absolutely crucial. It ensures there's a nice, steady stream of pressure feeding the valve, which lets it open cleanly and stay open until the danger is gone. Okay, on to the next puzzle. We've got our valve working perfectly now. It opens up and a massive wave of high-pressure fluid is rushing out. But where all that fluid goes creates a brand new obstacle. All that stuff has to go somewhere, usually through a huge network of pipes to a flare to be safely burned off. But that whole network of pipes isn't empty. It's already full of gas, and all that gas creates a force that literally pushes back against the new stuff trying to get in. That pushback is called back pressure.
And this shows you the conflict perfectly. You've got the PSV trying with all its might to push fluid out, but the flare system is pushing back. And if that back pressure gets too high, it can literally stop the safety valve from opening all the way, or even at all. It's like trying to open a door against a really strong wind.
So what's the fix? Well, you pick the right tool for the job. It turns out there are different types of PSVs, and they can handle different amounts of that pushback. Your standard everyday valve can only handle about 10% back pressure, but then you have a balanced bellows design that can take way more, up to 50%. And then there are these really advanced pilot-operated valves that can handle a staggering 70%. It's all about matching the right valve to the system it's protecting.
Okay, we're at the final challenge. The fluid is now screaming through the main collection pipe, the flare header. And in here, the speeds and the forces are so extreme, they can literally tear the piping apart from the inside out.
Now, for normal pipes, there are speed limits just to keep things from getting too noisy, as this quote from an industry standard points out. But a relief header is not a normal pipe. During an emergency, the speeds are just incredible. And trust me, noise is the very last thing you're worried about. The real fear is the raw, destructive force. To get a handle on this, engineers calculate something called momentum flux, or as they say it, rho v squared. The best way to think about it is as the fluid's punching power. It's a number that tells you how much force is slamming into every pipe elbow and T, causing violent vibrations that can crack welds and destroy supports. So the final safety check is really a two-part test. First, you limit the speed to a fraction of the speed of sound, its Mach number, to prevent sonic shock waves from forming inside the pipe. And second, you check that the momentum flux, that punching power, is below a critical threshold, so the pipe doesn't literally vibrate itself to pieces. These two rules make sure the whole system can actually survive the very thing it was built for.
So we've gone through a lot of technical stuff, but what's the big takeaway here? Well, these rules, they're not just numbers on a page. They are the actual language of safety. Let's just boil it down one more time. The pipe going into the valve is all about that 3% rule to stop chatter. The pipe coming out is sized to handle back pressure, depending on the valve you chose. And the main header pipe is designed to survive incredible force by limiting Mach number and that rho v squared value. 3 different parts of the system, 3 critical sets of rules. And that kind of leaves us with a bigger question, doesn't it? When you look at all these complex guidelines, it's easy to just see them as limits, as constraints on a design. But what if they're not? What if they're a language, one that's been built over decades of experience, designed for one purpose, to make sure that when everything else fails, the last line of defense actually holds?